Imagine you're carrying a heavy backpack on a hot summer afternoon. The heavier the load, the hotter your body becomes. Underground cables behave in the same way. When too much current flows through them, they begin heating up. And just like how your body has a limit for how much heat it can tolerate, cables also have a maximum permissible temperature rise that governs how much current they can safely carry. This temperature rise occurs because of the various losses inside the cable. Copper losses in the conductor, hysteresis losses in the dielectric, and eddy current losses in the sheath. All of these combine to generate heat. As current flows, heat builds up. If the cable can't get rid of this heat fast enough, its temperature rises. For typical underground installations, the safe working temperature usually reaches around 65 degrees Celsius for armored cables and around 50 degrees Celsius for lead sheath cables laid in ducts. When the heat produced inside the cable equals the heat dissipated to the surroundings, the temperature stabilizes. But when the heat cannot escape fast enough, the cable temperature rises and its permissible current must be limited. To properly calculate how much current an underground cable can carry, we must consider the thermal resistivity of the insulation, the protective coverings, and the soil. Before we move ahead, tell me in the comments, did you know that even soil type affects cable current rating? Clay, sand, and wet soil all pull heat away very differently. Let's see how this all connects. Think of heat flowing along a path exactly like water flowing through a pipe. If the pipe is narrow or blocked, the flow becomes difficult. This difficulty or obstruction in the movement of heat is what we call thermal resistance. By definition, thermal resistance is the temperature difference between 2 points divided by the heat flowing in a unit time between them. In SI units, heat flow is measured in watts. So, thermal resistance S is expressed as temperature rise, T divided by power dissipated P. Its unit becomes degrees Celsius per watt, and honestly, this is also known as a thermal ohm because its behavior is very similar to electrical resistance. Just as electrical resistance is directly proportional to the length of the path of current and inversely proportional to the cross-sectional area, thermal resistance behaves in exactly the same way for heat flow. So, thermal resistance increases when the path length increases and decreases when the area of heat flow increases. We can express this relationship as S is proportional to L divided by A, or more precisely, S equals K multiplied by L divided by A, where L is the length of the cable in the direction of the heat transmission, A is the cross-sectional area of the cable, and K is the thermal resistivity of the material. From this, thermal resistivity K can be written as S multiplied by A divided by L. The unit becomes thermal ohm meter. Isn't it interesting how heat behaves almost exactly like electricity? Did you ever imagine that before? Let me know in the comments. Now let's apply this concept to a real cable. Imagine we are looking at a cross-section of a single-core underground cable on the screen. The conductor is at the center, surrounded by layers of insulation. We want to determine the thermal resistance offered by this insulation. Let the radius of the core be R and the inside radius of the sheath be R1. The thermal resistivity of the insulation is K. Now, let's consider 1 meter length of the cable. We take a very small ring-shaped element of insulation at radius X, having thickness dx. The thermal resistance of this tiny element is expressed as K multiplied by dx divided by 2 pi x. To find the total thermal resistance of the insulation, we integrate this expression from radius r to radius r1. This eventually becomes K divided by 2 pi multiplied by natural logarithm of r1 divided by r. This value gives us the thermal resistance of the dielectric per meter length of cable. The thermal resistance of the lead sheath is extremely small, so in most cases it is safely neglected. Now let's relate all this thermal theory to the actual current that a cable can safely carry. Heat generated inside the cable must escape through several layers, first through the dielectric, then through the sheath, then through the bedding and armor, and finally into the surrounding soil. All these layers behave like thermal resistances connected in series, so the total thermal resistance is simply the sum of all these individual resistances. Okay, so if I denote the permissible current by I the number of conductors, by N the electrical resistance per meter of the conductor, by R the total thermal resistance, by S, and the maximum allowable temperature rise, by T, then the power generated inside the cable due to resistive losses becomes, well, N multiplied by I squared multiplied by R. This power, must equal the temperature rise divided by the total thermal resistance, which can be spoken as T divided by S. So, equating these two gives N multiplied by I squared multiplied by R equals T divided by S. Solving this for I gives the important formula for permissible current, which is expressed as I equals square root of T divided by NRS. This basically is the maximum current a cable can safely carry. And remember, if cables are laid very close to each other, heat dissipation becomes poor, and therefore the permissible current reduces. Let me know in the comments whether your plant or installation considers the spacing between cables to avoid mutual heating. Now let's solve the example as shown on the screen. A single core cable is laid underground. Its core diameter is 30 mm, and the insulation or dielectric thickness is 40 mm. The thermal resistivity of the insulation is 5 thermal ohm meter. The thermal resistance between the sheath and the ground surface is 0.45 thermal ohm per meter. The electrical resistance of the cable is 110 micro ohm per meter, and the permissible temperature rise is 55 degrees Celsius. Alright, so first, we calculate the thermal resistance of the dielectric. The core radius, R, becomes 15 millimeters because 30 divided by 2 equals 15. The inside radius of the sheath, R1, becomes 15 plus 40, which equals 55 millimeters. Now, using the expression we derived earlier, the thermal resistance of the dielectric becomes K divided by 2 pi multiplied by the natural logarithm of R1 divided by R. Substituting K equals 5, R equals 15, and R1 equals 55, we get approximately 1.03 thermal ohm per meter. Next, the thermal resistance of the soil and surrounding layers is already given as 0.45 thermal ohm per meter. Adding these two values gives a total thermal resistance of 1.48 thermal ohm per meter. Okay, now we apply the main current formula. I equals the square root of T divided by NRS. So, substituting T equals 55, N equals 1, R equals 110 multiplied by 10 to the power minus 6 ohm, and S equals 1.48. We get the final answer of approximately 581 ampere. That is the maximum permissible current for this underground single-core cable. If you've stayed with me till now, you've built a strong understanding of how underground cables carry current and how thermal limitations decide their capacity. Before we wrap up, I want to know from you, should I make a separate video explaining soil thermal resistivity with real field examples and practical measurement techniques? If you want it, just type yes in the comments. And as always, please like, share, and subscribe to Electrology. These detailed engineering videos take a lot of time and effort, and your support really helps the channel grow. Also, don't forget to check out the thanks button and the join button below. Even a small contribution from your side helps me continue creating in-depth electrical content like this. Your support truly keeps this channel alive. See you in the next video, only on Electrology.